There is an experiment so simple a child could draw it, and so strange that the greatest physicists of the last century could not agree on what it means. Welcome to the Sleepy Lab. Tonight, we begin at the very start of that strangeness. A quiet room in 1801. A beam of light and two narrow slits cut into a barrier. If you drift off before we reach the end, that is perfectly fine. The experiment will still be running when you wake. If these slow journeys through science help you rest, consider subscribing, one sleepy soul at a time. Now, let's begin. In 1801, a British physician and natural philosopher named Thomas Young set up a careful experiment in his study. He took a source of light and directed it toward a screen with two narrow slits cut side by side. On the far side of those slits, he placed another surface to catch whatever came through. What appeared on that surface was not what most people would have expected. It was not two bright lines, one behind each slit. It was a series of alternating bands, bright, then dark, then bright again, spreading outward like the pattern left by two stones dropped into still water. Young called them interference fringes, and they told him something that contradicted the most respected scientific mind of the previous century. Isaac Newton had believed that light was made of particles, tiny corpuscles. He called them traveling in straight lines. Newton's authority in natural philosophy was immense, and for much of the 18th century, his view held. But Young's fringes could not be explained by particles. Particles fired through two slits would simply pile up in two lines, one behind each opening. They would not spread. They would not cancel each other out. They would not produce darkness where you might expect light. Only waves could do that. Think of the surface of a calm lake. When two ripples meet, something happens at the place where they cross. If the high point of one ripple arrives at exactly the same moment as the high point of the other, they combine, the water rises higher than either ripple alone. That is constructive interference. But if the high point of one ripple meets the low point of the other, a crest meeting a trough, they cancel. The water at that point goes flat, as if neither ripple had passed through at all. That is destructive interference. And that is precisely what Young saw on his screen. Where the waves from the two slits arrived in step with each other, a bright band formed. Where they arrived out of step, darkness. Not dimness. Darkness. The light, in those places, had erased itself. The spacing of those bright and dark bands was not random. It followed a precise relationship, determined by the wavelength of the light and the distance between the two slits. Longer wavelengths produced wider fringes, shorter wavelengths, narrower ones. The pattern was orderly, predictable, mathematical. It was the signature of a wave, written in light on a screen. Young had not just contradicted Newton. He had given physics a new way of understanding what light was, or at least what it did. For nearly a century, the wave picture held. Light was understood as a disturbance moving through space, oscillating electric and magnetic fields, as James Clerk Maxwell would later describe them, propagating outward at a fixed and extraordinary speed. The interference fringes fit perfectly into this picture. And then, quietly, at the turn of the 20th century, something began to unravel. Physicists studying the interaction between light and metal noticed something they could not explain with waves. When light shines on certain metals, it can knock electrons loose from the surface. This is called the photoelectric effect. The strange part was not that it happened, but how it happened. If light were purely a wave, then a brighter wave, more intense light, should deliver more energy to the electrons and knock them free more easily. But that was not what the experiment showed. What mattered was not the brightness of the light, but its color. Low-frequency light, no matter how bright, could not dislodge electrons at all. High-frequency light, even at very low intensity, could. A wave spreading continuously through space could not explain this. In 1905, Albert Einstein offered an explanation. He proposed that light does not travel as a smooth, continuous wave. Instead, it travels in discrete packets of energy, individual bundles, each one carrying an amount of energy determined by its frequency. These packets would later be called photons. Einstein's explanation fit the photoelectric effect perfectly. The energy of each photon depended on the color of the light, not its brightness. A low-frequency photon simply did not carry enough energy to free an electron, no matter how many of them arrived. A high-frequency photon carried enough, even alone. It was a quiet but profound shift. Light, which Young had shown to be a wave, was also, somehow, a particle. This was not a small puzzle to be tidied away. It was a deep and genuine contradiction. The same entity, the same light that spreads through two slits and interferes with itself, also arrives at a detector as a single, localized point of energy. A wave is spread out. It occupies space. It overlaps and cancels. A particle is localized. It is here, not there. It does not spread. And yet, light appeared to be both. Not sometimes one and sometimes the other by accident, but both, depending on how you chose to look at it. Physicists had a word for this. Eventually, wave-particle duality. It is a careful, neutral phrase, and it is, in some ways, a placeholder for a deeper answer that has not yet arrived. It does not explain how something can be both. It simply acknowledges that something is. Young's experiment had begun with a straightforward question about the nature of light. And by the early 20th century, that question had opened into something far wider. Something that would draw in electrons and atoms and the structure of reality itself. Something that is still, as far as we can tell, unresolved. But that is where tonight's journey continues. For now, let the image rest gently in your mind. A screen in a darkened room. Two narrow slits. And on the far wall, a pattern of light and shadow that should not exist, and yet does. Bright bands where light has added to itself. Dark bands where light has quietly canceled itself away. The first whisper of a mystery that would take the next 2 centuries to deepen, and has not yet been answered. The trouble with light is that it refused to stay one thing. For a long time, the wave picture seemed sufficient. Young's bands of light and shadow had been reproduced, refined, extended. The mathematics of waves described light with quiet precision, and so physicists, for most of the 19th century, were reasonably content. Then came a small, stubborn problem. When light strikes a metal surface, it can knock electrons loose. This much was known, but the way it did so did not behave the way a wave should. A wave carries energy spread across its entire surface, the way a tide lifts a boat gradually, with patience. If light were purely a wave, then shining a dim light long enough should eventually dislodge electrons as the energy slowly accumulated. But that is not what happened. Dim light, no matter how long it shone, produced nothing, or almost nothing. And bright light of the wrong color produced nothing either. What mattered was not the intensity of the light, and not the duration. What mattered was the color, the frequency. Only light above a certain frequency could free electrons from the metal, and when it did, the electrons arrived immediately, without delay, as if struck by something discrete, something that delivered its energy all at once. In 1905, Albert Einstein offered an explanation. Light, he proposed, does not spread its energy continuously like a wave across water. It arrives in concentrated packets, each packet carrying a fixed amount of energy determined by its frequency. These packets would later be called photons. The mathematics worked. The predictions matched the measurements with care, and Einstein received the Nobel Prize for this work. Not for relativity, but for the photon. And yet, Young's interference pattern was still there, still forming on screens in laboratories, still showing the unmistakable signature of waves overlapping, canceling, reinforcing, a pattern that only waves can make. So light was a wave, and light was a particle. Not one or the other. Both, depending on how it was measured. The same beam of light that spread through two slits and interfered with itself could also arrive at a detector as a single, localized strike, a point, not a ripple. This was not a contradiction that could be resolved by looking more carefully. It was not a matter of incomplete instruments or imprecise measurements. The duality was real, and it was deep, and it sat at the center of physics like a quiet, unmoving stone. Physicists named it, as they often do when something resists explanation, wave-particle duality. The name did not dissolve the strangeness, it simply gave the strangeness somewhere to live. Then, in 1924, a young French physicist named Louis de Broglie made a proposal that extended the strangeness considerably. If light, which everyone had assumed was a wave, could also behave as a particle, then perhaps the reverse was also true. Perhaps matter, which everyone had assumed was made of particles, could also behave as a wave. De Broglie suggested that every moving object has a wavelength, not metaphorically, literally, a wavelength that depends on its momentum. The faster and heavier the object, the shorter the wavelength, until for everyday objects, the wavelength becomes so vanishingly small that it has no observable effect. But for something as light as an electron, moving at the speeds electrons move, the wavelength would be measurable. It was a quiet, almost audacious idea, proposed in a doctoral thesis, and it was, at first, difficult to know what to make of it. The confirmation came a few years later, from two independent sets of experiments. Electrons, directed at a crystalline surface, produced diffraction patterns, the same kind of patterns that X-rays, known waves, produced under the same conditions. The electrons were behaving as waves, bending, spreading, interfering with themselves as they passed through the regular spacing of atoms in the crystal. De Broglie had been right. Matter had a wavelength. An electron was not simply a tiny ball traveling in a straight line. It was something else. Something that spread and interfered and arrived as a point only when it was caught. And so, the double-slit experiment was tried again, this time not with light, with electrons. The setup was the same in principle. A source, two narrow slits, a screen to catch whatever arrived. But now the source fired electrons one at a time. A single electron, then a pause. Another electron, then another pause. Each one traveling alone, with nothing nearby to interact with. There was no beam, no crowd of particles that might somehow push against each other and create a pattern through their collective behavior. Just one electron at a time, crossing the apparatus in solitude. The first electron arrived at the screen and left a single mark, a point, exactly where a particle would land. The second electron arrived, another point, somewhere slightly different. And the third, and the fourth, each one a dot, seemingly random, scattered across the screen without obvious order. For a long time, watching the individual arrivals, there was nothing to see but noise, specks distributed without apparent meaning. But the experiment continued, patiently, hundreds of electrons, then thousands. And slowly, the pattern emerged. Not randomly distributed dots, not a simple smear centered behind each slit. The way marbles rolling through two holes would pile up in two heaps. Something else entirely. Bands, alternating regions of many arrivals and almost none. The same interference pattern that Young had seen with light more than a century before. Bright fringes and dark fringes, built up one electron at a time, over hours. Each electron had arrived as a particle, a single point on the screen, and yet accumulated across thousands of arrivals. They had arranged themselves into a pattern that only a wave can make. The only way to produce that pattern is through interference. Two waves, spreading from two slits, overlapping, adding in some places, and canceling in others. But there was only one electron at a time, nothing to interfere with. Unless the electron interfered with itself. Unless, somehow, a single electron passed through both slits simultaneously, spread as a wave through the entire apparatus, and then, upon arriving at the screen, resolved itself into a single point. This is not a comfortable idea. It does not fit the picture of a particle as a small, solid object traveling a single path. But the pattern on the screen does not leave much room for another explanation. The electron, it seems, does not take one path or the other. It takes both, or neither, or something for which ordinary language does not have a word. It exists between source and screen in a condition that is not quite wave and not quite particle, a condition that only becomes definite at the moment of arrival. And then it lands, a single point, as if it had always been a particle, as if the spreading, the interfering, the traveling of two paths at once had never happened. This result, single electrons building an interference pattern, one arrival at a time, is considered by many physicists to be the clearest window into the strangeness of the quantum world. Not because it is the most dramatic experiment, but because it is so simple. A source, two slits, a screen, and a question that the pattern on that screen asks without ceasing. Where was the electron before it arrived? The answer, as far as anyone can tell, is that the question may not have a clean answer. The electron was not in one place, traveling one path. It was in a condition that our ordinary sense of location does not quite describe. And that condition, whatever it is where tonight's story goes next. That condition has a name, of a kind. Physicists call it superposition. The word sounds technical, almost cold, but what it points to is something quietly extraordinary. It describes a state in which a particle has not yet settled into a single definite reality, where it holds multiple possibilities at once, not as a matter of ignorance, but as a matter of fact. The single electron experiment is considered by many physicists to be the most direct demonstration of superposition ever performed. Not a thought experiment, not a mathematical abstraction, but something you can watch accumulate, dot by dot, on a screen. Each electron arrives as a particle, and yet the pattern they build together could only have been made by something that traveled as a wave. Both things are true, and they do not resolve into a comfortable middle ground. They simply coexist. Richard Feynman, one of the most careful thinkers physics has ever produced, said something about this experiment that has stayed with physicists ever since. He said that the double-slit experiment contains the only mystery of quantum mechanics. Not one of the mysteries, the only one. His meaning was precise. Every other strange phenomenon in the quantum world, every counterintuitive result, every paradox, every place where ordinary intuition fails, is, in some sense, a variation of what happens here, between a source, two slits, and a screen. That is a quiet and serious claim. It means that if you understood, truly understood, what happens in this experiment, not just the mathematics, but the reality behind it, you would understand the deepest layer of what nature is doing at its smallest scales. No one has fully understood it yet, and the experiment did not stay with electrons. Once physicists confirmed that a single electron could interfere with itself, a natural question followed. How far does this go? Is this a peculiarity of electrons, or something more general? The answer, as experiments accumulated over the following decades, turned out to be something more general. Neutrons were sent through double slits. They produced interference patterns. Whole atoms were sent through. They produced interference patterns. Then molecules, small ones at first, a handful of atoms bound together, were sent through, and they too arrived in the familiar alternating bands of more and less. Each time, the result was the same. The interference pattern, patient and precise, waiting on the other side. But researchers kept asking the question further. In 2019, a team of physicists produced interference fringes using molecules containing roughly 2,000 atoms each. 2,000 atoms, moving together as a single object through a pair of slits. And on the screen beyond, the pattern appeared. Faint, carefully measured, but unmistakably there. These are among the largest objects ever shown to behave as waves. Objects large enough that, in another context, you might almost call them specks of dust. And yet they spread, and overlapped, and interfered with themselves, just as a single electron does. The boundary between the quantum world and the ordinary world, the world of objects that simply are where they are, is not where common sense would place it. It may not be a sharp boundary at all. There is something worth resting with here, before the story moves on. The interference pattern is not a curiosity. It is a kind of testimony. It is the screen's way of recording that something wave-like passed through both slits, that the arriving object was, in some sense, in two places at once during its journey. And for a long time, physicists simply watched this pattern form and asked what it would take to understand it better. What if, they wondered, we simply looked? What if we placed a small detector at one of the slits? Not to disturb the particle, not to stop it, just to know which way it went. To answer the question, the pattern seems to be asking. The answer to that question changed everything. When a detector is placed at either slit, a device capable of registering which path the particle took, the interference pattern disappears. Completely. Not diminished, not blurred, gone. In its place, two simple bands appear on the screen, one behind each slit. Exactly what you would expect if the particles were ordinary objects, traveling one path or the other, with no wave behavior at all. The act of measuring the path removes the interference. This result has been repeated many times, in many forms, and it holds without exception. But the detail that physicists find most difficult to set aside is this. The pattern disappears even if the detector never displays its result. Even if no one reads the measurement, even if the data is never recorded anywhere a human eye could find it, even if the detector simply registers the information and that information sits, unexamined, in some component of the apparatus, the pattern is still gone. What matters is not whether anyone looked. What matters is whether the information about the path exists anywhere in the physical world. Whether it could, in principle, be known. The mere possibility of knowing is enough. This is the part of the experiment that tends to sit with people. It is not that a conscious observer collapses the wave. It is something stranger and more impersonal than that. It is that the physical availability of which path information, the fact that the universe now contains a record of which way the particle went, is sufficient to dissolve the interference. The pattern does not disappear because someone is watching. It disappears because the path has become, in some physical sense, a fact. And a particle whose path is a fact cannot also be a wave spreading through both slits at once. There is a stillness in this result, if you let it settle. The electron, traveling toward the slits, exists in that open condition, neither here nor there, neither this path nor that one. And the screen receives it as a wave, adding its small mark to a pattern that only emerges over thousands of arrivals. But the moment the apparatus knows which way it went, not a person, not a mind, just the apparatus, that openness closes. The electron becomes a particle with a history. And the pattern, which was the signature of its not having a history, quietly vanishes. What this means, what it really means, at the level of what is actually happening in the world, is something physicists have been debating for nearly a century. The mathematics describes it precisely, the experiments confirm it without ambiguity. But the interpretation, the story you would tell about what is taking place, remains genuinely open. And the stories that have been proposed are each, in their own way, as strange as the experiment itself. That is where this night's journey goes next. into the attempts to explain, each one careful, each one internally consistent, each one pointing at the same set of facts, and each one asking something of ordinary understanding that ordinary understanding finds very difficult to give. The first story begins with something that sounds almost too simple. A detector is placed at one of the slits. Not a person watching, not a camera with a screen anyone is reading, just a physical device, a small arrangement of matter, capable of registering which way the particle went. And the interference pattern disappears? Not partially, not faintly. It disappears completely, as if it had never been there. This is called the observer effect, and the name, though it has stayed, carries a small misleading weight. Because the observer, in this context, is not a mind. It is not awareness, or attention, or consciousness of any kind. It is simply a physical interaction that leaves a record. Any interaction that encodes which path information in any physical system, anywhere, produces the same result. The pattern goes. What seems to matter is not whether anyone looks. What seems to matter is whether the information exists to be looked at. That distinction is quiet, but it is very deep. Think of it this way. The electron, traveling toward the two slits, carries within it a kind of openness. It is not yet committed to a path. That openness is real. It is what produces the interference, the wave behavior, the pattern of light and dark that builds slowly across thousands of arrivals. But the moment a record is made, the moment the world, in any corner of itself, contains the answer to the question of which way it went, that openness resolves. The electron had a path. It was always going to have a path. And the wave, which was the shape of its not yet having one, is gone. The information does not need to be read. It does not need to be processed, or understood, or even accessible in any practical sense. Its mere existence, encoded somewhere in the physical state of the apparatus, is enough. This is one of the places where quantum mechanics becomes genuinely difficult to hold in the mind, because we are used to thinking of information as something that lives in minds, something that requires a reader. But here, information seems to have a kind of physical weight of its own, a causal power that operates independently of whether any conscious being ever encounters it. And then the experiment goes one step further. If the which path information can be erased, if the record is destroyed before any measurement of the final screen is made, the interference pattern can be partially recovered. This is called quantum erasure, and it is, in its quiet way, one of the stranger things that has ever been demonstrated in a laboratory. The particle has already passed the slits. The record was made, and then the record was unmade, and something of the wave behavior returns. What this suggests is subtle. It is not that erasing the record somehow reaches back and changes what the particle did. The particle's journey is over. What changes is the availability of the information. When the which path record exists, the interference is gone. When it is destroyed, when the world no longer contains the answer to which way it went, the interference, in the right experimental conditions, begins to reappear. The experiment is not asking about the particle's physical disturbance. The detector, even a gentle one, does interact with the particle in some small way, but careful versions of the quantum eraser have shown that the physical disturbance alone is not what destroys the pattern. It is the information, the knowability of the path. That is what the interference responds to. This is the point at which John Wheeler arrived in 1978 with a thought experiment that has since been carried out in real laboratories. Wheeler asked a simple question: what if the choice to observe or not to observe, to place the detector or leave it absent, is made after the particle has already passed through the slits? Not before, after. The particle is already in flight. It has already, in some sense, encountered the two openings. And then, in that moment, the experimenter decides whether to look. In delayed choice experiments, the particle's behavior appears to depend on that decision. If the experimenter chooses to measure which path was taken, The particle behaves as though it always had a definite path. If the experimenter chooses not to measure, the interference pattern builds as though the particle traveled both ways at once. And the choice was made after the particle was already past the slits. This does not mean the particle travels backward in time. Wheeler was careful about this, and the physicists who have tested his idea since have been careful too. There is no signal moving into the past, no cause following its effect in reverse. What it means, or what it seems to mean, is something harder to say plainly. Quantum events resist being assigned a definite history before measurement. The particle does not have a story, wave or particle, this path or that one, until the conditions of measurement are set, and those conditions can be set after the particle is already in motion. The past, at the quantum scale, is not fully written until the present decides to read it. That sentence is difficult. It should be. It is not a poetic flourish, it is a careful attempt to describe what the experiments actually show. And the experiments have been performed with photons traveling across optical benches, and in more recent years across distances of kilometers, with the delayed choice made by fast random number generators that could not have been anticipated by any hidden mechanism in the particle's preparation. The results hold. So here is where the night rests for a moment, not at an answer, but at the shape of the question. The interference pattern appears when no path information exists. It disappears when path information is recorded. It partially returns when that information is erased, and the particle's behavior seems to depend on choices made after it has already passed the point where the choice should have mattered. All of this is confirmed, repeated, precise, and none of it, taken together, tells us what is actually happening. The mathematics handles it without difficulty. The wave function evolves, and the probabilities it encodes match every result, every time, to extraordinary precision. But the wave function is a mathematical object. It tells us what we will find when we measure. It does not, on its own, tell us what is there when we are not measuring. That gap between the calculation and the reality is where the interpretations live. Each one is an attempt to fill that gap with something coherent, something that does not contradict the mathematics, does not contradict the experiments, and yet gives some account of what is actually taking place in the world when a particle moves through two slits and no one is watching. The Copenhagen Interpretation says the question itself may be unanswerable. Many worlds says every outcome happens somewhere. Pilot wave theory says the particle always had a path, guided by something real and non-local, moving through space. Each of these is a serious proposal. Each has been developed with care by serious people. And each one, when you follow it far enough, arrives at something that asks more of ordinary understanding than ordinary understanding was built to give. That is where this night continues. Quietly, without urgency, into the stories themselves. Begin with the delayed choice result and what it quietly implies. A particle leaves its source, passes through the apparatus, and somewhere in that journey, before any measurement has been made, its story is not yet written. That is the gentle strangeness the delayed choice experiment leaves behind. Not that time runs backward, not that causes follow effects in reverse. The mathematics does not support that, and the experiments do not suggest it. What it suggests is something quieter, and in some ways, more unsettling. It suggests that a quantum event does not have a definite history until something fixes it in place. The particle does not travel as a wave and secretly remember which slit it used. It does not carry a hidden record of its path, waiting to be read. As far as the experiment can tell, as far as any experiment has ever been able to tell, the path simply was not one thing or another until the moment a measurement made it so. The past, at the quantum scale, may be less settled than it appears. That thought can rest here, without being pressed further. It does not need to be resolved tonight. It only needs to be held, lightly, the way one holds something delicate in an open hand. The Copenhagen Interpretation begins here, in this same unresolved place. It was shaped, mostly, In the 1920s, by two men working in close conversation with each other and with the experiments that kept refusing to behave. Niels Bohr was a Danish physicist with a gift for sitting with contradiction. Werner Heisenberg was younger, more mathematical, and arrived at some of the same conclusions by a different road. Together, and with others around them, they built what became the dominant way of thinking about quantum mechanics for most of the 20th century. Their answer to the strangeness was, in a sense, to accept it completely. Under the Copenhagen Interpretation, a particle does not have a definite position before it is measured. It does not have a definite momentum. It does not have a definite path through the two slits. These are not properties waiting to be discovered. They are properties that do not exist until the act of measurement calls them into being. This is not a claim about ignorance. It is a claim about reality. The wave function, under Copenhagen, is not a map of something hidden beneath the surface. It is not a placeholder for information we have not yet gathered. It is the complete description of what exists, the full truth of the particle's situation before observation. And that truth is a spread of possibilities, not a single fact. When measurement occurs, one possibility becomes actual. The others do not, and the wave function, which held all of them at once, gives way to the single outcome that was found. Bohr was careful about what he would and would not say. He would say, "Here is what the particle does when measured. Here is the probability of each result. Here is how to calculate it, and the calculation will be correct." He would not say, "Here is what the particle is doing between measurements." That question, he argued, is not a scientific question at all. It is not that the answer is hidden or difficult to reach. It is that the question itself reaches beyond what physics can meaningfully address. To ask what the electron is doing when no one is looking is to ask for a description that no experiment could ever confirm or deny, and a description that no experiment could ever test is not, in Bohr's view, part of science. This is a position that some find deeply satisfying, and others find deeply unsatisfying. It is honest about the limits of what can be known. It does not invent stories to fill the silence, but it also leaves the silence intact, and some minds find that silence harder to rest in than others. Heisenberg arrived at his own piece of this picture through a different door. He was working on the mathematics of quantum systems in the mid-1920s when he noticed something that the equations seemed to be insisting on. Position and momentum cannot both be precisely known at the same time. Not because the instruments are too crude, not because the measurements disturb each other in some mechanical way that better technology might one day correct, but because the universe, at the quantum scale, does not permit both to be simultaneously definite. The more precisely a particle's position is pinned down, the more its momentum becomes spread across a range of values. The more precisely its momentum is known, the more its position dissolves into uncertainty. This is not a trade-off imposed by measurement. It is a feature of what the particle is. The uncertainty principle, as it came to be called, is written into the structure of quantum mechanics at a level that cannot be removed. It follows from the mathematics with the same inevitability as any other consequence of the theory, and it has been confirmed, quietly and repeatedly, in every experiment that has ever tried to press against it. There is a way to feel this without the mathematics. A wave that is perfectly localized, a sharp spike at one point in space, is built from an enormous range of frequencies, many different wavelengths, all added together, canceling everywhere except at that one point. And wavelength, through de Broglie's relation, is connected to momentum. So a particle with a very precise position must be composed of a very wide spread of momenta. A wave with a single precise frequency, a pure, smooth oscillation, extends across all of space without a definite location. It is everywhere and nowhere in particular. Its momentum is exact, but its position is entirely open. These are not separate facts. They are the same fact, seen from two directions. Position and momentum are not independent quantities that happen to interfere with each other. They are complementary aspects of a single underlying description, and the precision of one is always purchased at the cost of the other. Bohr called this complementarity, the idea that certain pairs of properties are not simultaneously real in the way that everyday objects seem to be, that the wave nature and the particle nature of a quantum object are not contradictions to be resolved, but complementary faces of something that ordinary language was not built to hold. A particle moving through two slits is not secretly a wave pretending to be a particle, or a particle pretending to be a wave. It is something that becomes one or the other depending on how it is encountered. And between encounters, it is neither, or both, or something for which there is no word. This is the Copenhagen Interpretation, stated as plainly as it can be stated. It does not tell a story about what happens in the dark. It tells a story about what happens when the lights come on. And it insists, with quiet firmness, that the story of the dark is not a story physics can tell. Many physicists have lived comfortably inside this view for a century, using the formalism, trusting the predictions, setting aside the deeper questions as unanswerable and therefore not worth losing sleep over. Others have found that impossible, have felt that a theory of the world ought to say something about the world, not only about measurements of it, and from that discomfort, other interpretations grew. But those come later. For now, there is only this: a particle with no definite position, a momentum that cannot be fully known while the position is held, a wave function that is not a map of something hidden, but the whole of what is real before the moment of looking, and the quiet suggestion that the universe, at its smallest scales, does not keep records of where things were when no one was there to ask. That thought settles slowly, like dust in still air, like the last light fading at the edge of a room. The wave function. It is worth sitting with that phrase for a moment, not rushing past it, because it is the central object of all of quantum mechanics, and it is stranger than it first appears. A wave function is a mathematical description. It is written as an equation, evolved according to precise rules, and it encodes, for any quantum system, the full range of states that system might be found in, not the state it is in, the states it might be found in, and with what probability when someone or something finally looks. Think of it this way. Before measurement, a particle does not have a position the way a stone resting on a table has a position. It has a spread, a kind of weighted map of possibilities, some more likely than others, none of them settled. The wave function holds all of that. It carries the whole landscape of what could be, rippling forward through time according to an equation called the Schrödinger equation, smooth and continuous and perfectly deterministic. And then something happens. A measurement is made. A detector fires. A particle arrives at a screen. And in that instant, the entire spread of possibilities resolves into one, a single outcome, definite and irreversible. The particle is here, not there. This energy, not that one. The landscape collapses to a single point. This is what physicists call wave function collapse. And it is where the trouble begins. The Schrödinger equation, which governs how the wave function evolves, is a beautiful piece of mathematics. It is linear, continuous, and it does not collapse anything. It simply carries the wave function forward, all possibilities intact, spreading and interfering and evolving without interruption. There is nothing in the equation that says, now stop, now choose, now become one thing. The collapse is not derived from the theory. It is added to it. Physicists call it a postulate, a rule that is assumed rather than explained. When a measurement occurs, the wave function collapses. That is the rule. But the equations themselves are silent on why, or how, or precisely when. They do not describe the transition. They simply stop applying, and the rule takes over, and a single outcome appears. This silence has a name. It is called the measurement problem. And it is not a small gap. It is not a detail waiting to be filled in by a more careful calculation. It sits at the very center of the theory, between the smooth world the equations describe and the definite world that measurements reveal, between the wave and the particle, between the possible and the actual. For nearly a century, this gap has remained. Some physicists have argued it's not a real problem, that the wave function is simply a tool for calculating probabilities, and asking what happens during collapse is like asking what happens to a weather forecast after the rain arrives. The forecast was never the rain, it was only ever a description of likelihood. And once the outcome is known, the description is updated. Nothing physical has occurred. Others have found that answer insufficient. If the wave function is only a calculation tool, then what is the theory actually describing? What is the world made of, underneath the mathematics? These questions do not go away simply because the formalism works. And so the measurement problem remains, quietly, persistently, one of the deepest unresolved questions in the foundations of physics, not at the edges of the theory, but at its heart. In 1957, a young physicist named Hugh Everett offered a different way of seeing it. He was a graduate student at Princeton at the time, and his proposal was, in its own way, the most radical response to the measurement problem that anyone had yet put forward. Everett asked a simple question. What if the wave function never collapses? Not, what if collapse happens differently than we thought? Not, what if collapse is caused by some mechanism we haven't found yet? But simply, what if it doesn't happen at all? What if the Schrödinger equation is always right? What if it applies not just to particles, but to detectors and laboratories and physicists and everything else? What if the wave function of the entire universe simply continues to evolve, smooth and unbroken, and nothing is ever selected, and nothing is ever lost? The answer Everett arrived at was this. Every possible outcome of every measurement occurs, not one after another, not in some hidden layer of reality, but simultaneously, in branching versions of the world that split apart at the moment of measurement and never interact again. When a particle reaches a detector, the detector does not register one outcome. It registers all of them. But each outcome occurs in a separate branch, and the observer in each branch experiences only their own result, with no access to the others. From inside any single branch, it looks exactly like collapse. One outcome, definite, irreversible. But from outside, from the perspective of the full wave function, nothing collapsed at all. Everything continued. This is the many-worlds interpretation, and it resolves the measurement problem in a precise sense. There is no collapse to explain, because there is no collapse. The equations are always right. The wave function always evolves smoothly. The branching is simply what that smooth evolution looks like when it includes observers. The cost of this resolution is not mathematical. The mathematics is clean. The cost is something harder to hold. It means that every quantum event with more than one possible outcome produces a branching, every radioactive decay, every photon absorbed or reflected, every electron arriving at a screen, each one a quiet fork in the structure of reality, each branch equally real, equally present, equally continuing forward in time. The other outcomes do not disappear. They simply become inaccessible, separated from this branch by a gap that no signal can cross and no measurement can bridge, permanently, irrevocably elsewhere. How many branches there are is not a question the theory answers simply. Possibly an enormous number. Possibly, in some sense, without limit. The theory does not forbid it, and the mathematics does not constrain it. Many physicists find this difficult to accept, not because it is mathematically inconsistent, it is not, but because it asks for a great deal. It asks that we take seriously the existence of realities we can never observe, never test, never reach. And it asks that we accept this not as speculation, but as the literal content of the most successful physical theory ever written. Others find it the most honest reading of the equations. If the Schrödinger equation is always right, they say, then this is what it implies. Not as a metaphor, as a description of what is. The many-worlds interpretation is taken seriously by a significant number of working physicists. It is not a fringe view, it is a genuine contender. and yet it remains contested because the questions it raises about probability, about identity, about what it means to be one observer in one branch, have not all been answered to everyone's satisfaction. So here's where things stand. The wave function evolves smoothly, precisely, according to equations that have never been wrong. And then a measurement occurs and a single outcome appears. And the theory, in its standard form, cannot say how that transition happens, only that it does. One response is to accept the silence, to use the formalism and not ask what lies beneath it. Another is to say the transition never happens at all, that every outcome is real, somewhere, in a branch of the wave function that continues quietly on its own. Both of these are serious positions. Both are held by serious people, and neither has been ruled out. The night holds that uncertainty gently. It does not press for resolution. It simply lets the question rest, unanswered, as it has rested for decades, in the same quiet way that a wave function rests before measurement, spread across all its possibilities, waiting. David Bohm arrived at his theory in 1952. He was not the first to think along these lines. Louis de Broglie had sketched something similar in the 1920s. Around the same time, the Copenhagen Interpretation was taking shape, but de Broglie's idea was set aside, quietly, as the field moved in a different direction. Bohm returned to it, worked it through more carefully, and arrived at something complete. The theory is called pilot wave theory, and it begins with a different premise than many worlds, a quieter premise. In some ways, it says that particles are real, always real. A particle passing through the double-slit apparatus has a definite position at every moment. It travels a precise path. It does not spread out into a cloud of probabilities. It does not exist in superposition. It simply moves. But it does not move alone. Alongside the particle, woven through the same space, filling the same experimental chamber, there is a wave. A real, physical wave. Not a wave of probability, not a mathematical convenience, but something Bohm treated as genuinely present in the world. This is the pilot wave, and it guides the particle the way a current guides a leaf on water. The leaf has a definite position, but where it goes depends entirely on the shape of the water beneath it. The pilot wave passes through both slits at once. It spreads, it overlaps, it interferes with itself in the space beyond the barrier, and the particle, following the contours of that wave, is steered toward the bright regions and away from the dark ones. Over many particles, each guided by its own pilot wave. The pattern that accumulates on the screen is exactly the interference pattern that experiments produce. The same bands, the same spacing, the same quiet geometry. And when a detector is placed at one of the slits, the wave changes. The act of measurement alters the pilot wave's shape, and the particle's trajectory changes with it. The interference pattern disappears, not because the particle was disturbed in some vague sense, but because the wave that was guiding it has been reshaped by the interaction. The mathematics follows through precisely. Every prediction of standard quantum mechanics is reproduced. This is what makes pilot wave theory remarkable. It gives back something that the Copenhagen Interpretation deliberately set aside. It gives back a picture, a story of what the particle is doing between measurements. In Copenhagen, that question was declared unanswerable, perhaps even meaningless. In pilot wave theory, it has an answer. The particle was here, then here, then here, following a path that was always definite, always real, even when no one was watching. And yet the pilot wave itself carries a strangeness of its own. Because the wave does not travel at the speed of light, it does not travel through space the way ordinary waves do. It responds to changes in the experimental setup, the opening or closing of a slit, the placement of a detector, essentially without delay, across whatever distance separates the particle from the change. This is what physicists call non-locality, a kind of instantaneous connection that reaches across space. It does not allow information to travel faster than light. The mathematics ensures that no signal, no message, No usable communication can be sent by exploiting the pilot wave's non-locality. And yet the connection is there. The wave knows, in some sense, about the whole experimental arrangement at once. It is not local. It is not confined to the neighborhood of the particle. It extends. Some find this troubling. Others find it clarifying, because Bell's theorem, proved in 1964, showed that any theory reproducing the predictions of quantum mechanics must be non-local in some form. There is no escape from that. The pilot wave theory does not hide this fact. It makes it explicit. The non-locality is built into the structure of the wave, visible and acknowledged. So here are two very different responses to the same mystery. Many worlds says the wave function is everything. It never collapses. Every outcome occurs. The universe branches, quietly and completely, at every measurement, and each branch continues on its own. The particle that went left and the particle that went right are both real. They simply inhabit versions of the world that can no longer reach each other. Pilot wave theory says the particle is real, and the wave is real, and the particle always goes one way. Left or right? Definitely one. The other path is not taken. There is no branching. There is only the particle, and the wave that guides it, and the path that was always there to be followed. Both of these reproduce every experimental result. Both are mathematically consistent. Both are taken seriously by physicists who have spent careers thinking carefully about these questions, and both carry their own weight of strangeness. Many worlds asks you to accept that every possible outcome is real, somewhere, in a proliferation of branches that may be infinite in number. Pilot wave theory asks you to accept a wave that fills all of space, responds instantaneously to distant changes, and yet remains forever hidden from direct detection. Neither asks less of you than the other. They simply ask different things, and this is part of what makes the double-slit experiment so enduring. It is not just a demonstration of quantum behavior, it is a kind of mirror. Each interpretation of quantum mechanics looks into it and sees something different. Copenhagen sees the limits of what can be asked. Many worlds sees a branching tree of equal realities. Pilot wave theory sees a particle on a guided path, accompanied always by a wave it cannot escape. The experiment itself does not choose between them. It simply produces its pattern, the same pattern it has always produced. Bright bands and dark bands, spaced according to the wavelength, appearing gradually as particle after particle arrives and settles into its place. The pattern does not care which interpretation is correct. It only asks to be explained. And the explanations keep coming. Each one careful, each one internally consistent, each one carrying something the others do not. There is a kind of patience in that, a willingness to sit with the question rather than force it closed. The physicists who work on these foundations are not confused. They are precise. They simply disagree about what the precision is pointing toward. The many worlds interpretation requires no collapse, no special mechanisms, no additional postulate, no moment where the smooth evolution of the wave function is interrupted. It is, in that sense, the most minimal response to the measurement problem. It adds nothing to the equations. It only takes the equations seriously, all the way down, without flinching at what they imply. And what they imply is an enormous proliferation of worlds, each one equally real, each one permanently sealed from the others after the moment of branching. That sealing is total. The branches do not interact. The version of you that observed one outcome and the version that observed another are, from the moment of measurement onward, as separate as 2 points in space that are moving apart faster than light can cross between them. Not destroyed, not diminished, simply unreachable. There is something almost restful in that image. Each branch continuing, each outcome finding its place in a version of the world that holds it. Nothing lost. Exactly. Only separated. The wave function, vast and unbroken, carrying all of it forward. And the pilot wave, meanwhile, moves through its own kind of space. Quiet, precise, guiding each particle along a path that was always there. The interference pattern emerging not from mystery, but from the shape of the wave, from the geometry of what the wave has become after passing through both slits and folding back on itself. Both pictures are still open. Both are still being worked on, refined, tested against new experiments, argued over in careful language by people who find the question genuinely important. The night does not resolve it. It only holds it, the way it holds everything that has not yet found its answer. Gently and without hurry. And the pilot wave does not stop at the slits. It fills all of space. Every corner of the experimental setup, every region the particle might conceivably reach, the wave is already there, already shaped by the geometry of the apparatus, already aware, in whatever sense a wave can be aware, of whether one slit is open or two. This is one of the stranger features of the pilot wave picture. When you close one of the slits, the wave changes. Not gradually, not after some signal has traveled from the slit to wherever the particle happens to be, but immediately. The whole wave, everywhere at once, rearranges itself to reflect the new configuration. The particle riding that wave follows a path that was shaped by something that responded to a change before any ordinary signal could have carried the news. This is what physicists mean when they say the pilot wave acts non-locally. Non-locality is a word that sounds technical, but the idea it points to is almost simple. It means that something happening here can be connected to something happening there, not through a signal traveling between them, not through any chain of cause and effect moving at the speed of light or slower, but through a kind of immediate, unmediated relationship that does not respect the ordinary rules of distance. The pilot wave requires this. It is not optional, not a feature that might be refined away in a later version of the theory. The non-locality is built into the structure of what the wave is and how it behaves. And yet, this non-locality cannot be used to send a message. You cannot exploit the instantaneous response of the pilot wave to transmit information faster than light. The mathematics closes that door carefully. What the wave does instantaneously is real, but it arranges itself in a way that keeps the outcomes, on their own, from carrying any signal you could read. It is a strange kind of connection. Present, but silent. Immediate, but unreachable as a channel. The pilot wave knows, in some sense, the shape of the whole experiment at once, and it guides the particle accordingly, but it does not let you use that knowledge to reach across space and touch something distant. This tension between the non-locality that seems to be required and the impossibility of using it runs through much of what came after. Because the pilot wave is not the only place where non-locality appears. In 1964, a physicist named John Bell sat down with a question that had been quietly waiting since the 1930s. The question, roughly, was this: could there be a deeper theory beneath quantum mechanics, one in which particles have definite properties all along, properties that are simply hidden from us until we measure them, that would explain the strange correlations quantum mechanics predicts without requiring anything non-local? Einstein had hoped for something like this, a theory in which the apparent randomness of quantum outcomes was not fundamental, but merely a reflection of our ignorance, hidden variables waiting to be found. Bell found a way to test the idea. Not directly, you cannot test what is hidden by definition, but mathematically, he showed that any theory in which particles carry definite hidden properties, and in which those properties are determined locally, without instantaneous connections across space, must obey certain statistical limits. Limits on how strongly the outcomes of measurements on distant particles can be correlated. He wrote down an inequality, a precise mathematical boundary, and he showed that quantum mechanics predicts correlations that cross that boundary. If quantum mechanics is right, then no local hidden variable theory can be right. The two are incompatible. You must choose. Either the world is non-local, things here are immediately connected to things there in ways that do not travel through space, or particles do not have definite properties before they are measured. Or both. Bell's theorem did not tell you which. It only told you that at least one of those things must be true. That the comfortable picture of a world made of objects with fixed properties, each minding its own local business, cannot survive contact with what quantum mechanics actually predicts. This was a theorem, a proof, not an experiment, not yet, but it opened a door that experimenters could walk through. And they did. Beginning in the 1970s, physicists began testing Bell's inequality in the laboratory. The experiments used pairs of entangled particles, particles whose quantum states are linked in such a way that measuring one seems to instantly affect what you find when you measure the other, no matter how far apart they are. The results came back, again and again, on the side of quantum mechanics. The correlations were stronger than any local hidden variable theory could produce. Bell's boundary was crossed, consistently, in experiment after experiment. The most careful and widely cited of these early tests was carried out by Alain Aspect and his colleagues in Paris. In 1982, Aspect's experiment used pairs of photons, produced together and then sent in opposite directions. Measurements were made on each photon separately, with the choice of what to measure changed rapidly, quickly enough that no signal traveling at the speed of light could have carried information from one measurement to the other before the second measurement was made. And still the correlations held. Still the results on the two sides matched in ways that exceeded what local hidden variables could explain. The experiment was not perfect. No experiment is. And physicists spent the following decades identifying and closing what they called loopholes, ways the result might, in principle, have been produced by something other than genuine non-locality. Each loophole, carefully closed, returned the same answer. By the time the most rigorous tests were completed, in the 2010s, the conclusion was difficult to avoid. The world, at the quantum level, is not locally real in the way that common sense suggests. Either distant events are connected in ways that do not travel through space, or particles do not have definite properties independent of measurement, or some combination of the two. Bell had not told us which picture was correct. He had only told us which pictures were ruled out. And the ones that remained were all, in their different ways, strange. The pilot wave keeps its particles real, keeps their positions definite, but pays for that with non-locality, with a wave that reaches everywhere at once. Copenhagen keeps its silence about what exists before measurement, and in that silence avoids the question of non-locality almost entirely. Many worlds branches quietly, carrying all outcomes forward, and handles the correlations through the structure of the wave function itself, without requiring anything to travel between the branches at all. Each of these is a coherent response to what Bell proved. Each accepts the constraint in a different way. Each gives up something different in order to remain consistent. And none of them has been ruled out. The experiments tell us what the world is not. They do not yet tell us what it is. There is something almost peaceful in that. The question is not unresolved because no one has thought carefully enough, or worked hard enough, or built precise enough instruments. It is unresolved because the answer, whatever it is, requires giving up something that feels fundamental. And different physicists, reasoning carefully from the same evidence, find themselves willing to give up different things. The night holds all of it. The pilot wave, filling space. Bell's inequality, drawn in careful mathematics. The photons in Aspect's laboratory, traveling in opposite directions, still correlated in ways that should not be possible. And the question, patient as it has always been, still open. There is one more thread to follow before the night grows still. It begins with two particles. Not two separate things, exactly, but two particles that have interacted in such a way that they can no longer be described on their own. Each one carries, woven into its quantum state, a reference to the other. They are, in the language of physics, entangled. What that word means is quiet and strange. It means that if you were to measure one of them, say, the direction of its spin, you would instantly know something about its partner. Not approximately, not probably. Exactly. The moment one particle is measured and found to be spinning one way, The other is found to be spinning the opposite way, every time, without exception. And the distance between them does not matter. They could be on opposite sides of a laboratory. They could be on opposite sides of a city. As far as the experiments have been able to test, the correlation holds regardless of how far apart the two particles have traveled since they last touched. This is not a subtle effect. It is not a statistical tendency or a rough approximation. It is a precise, repeatable, experimentally confirmed feature of the world. Two particles, separated by space, sharing a property that neither one possessed alone until the moment of measurement. Einstein found this deeply troubling. He had spent his life building a picture of reality in which things that are far apart cannot influence each other without something passing between them. Some signal, some carrier, some physical connection moving through space at a finite speed. That picture felt, to him, like the only reasonable foundation for physics. Entanglement seemed to violate it. He called it, in a letter, spooky action at a distance. The phrase carries a kind of quiet unease, not wonder. Exactly, more like the feeling of noticing something that should not be there. Einstein did not believe the universe was actually doing this. He believed, instead, that quantum mechanics was incomplete, that there were hidden variables, properties the particles carried all along, like instructions written before the experiment began, and that these hidden variables, once discovered, would restore the orderly, local picture of reality he trusted. In 1935, he wrote a paper with Boris Podolsky and Nathan Rosen. It is known by their initials, EPR. The argument was careful and precise. If quantum mechanics is correct, they wrote, then measuring one particle instantly affects the state of another, no matter how far away. But if no signal can travel faster than light, then the second particle must have carried the answer with it all along. And if it carried the answer all along, then quantum mechanics, which assigns no definite value before measurement, must be missing something. It was a serious argument. For nearly 3 decades, it remained largely unanswered, not because physicists ignored it, but because the question seemed, to many, unanswerable in practice. How would you ever test whether the particles carried hidden instructions, or whether the correlations were genuinely produced at the moment of measurement? Then, in 1964, John Bell found a way. He showed, through careful mathematics, that the two possibilities, hidden variables versus genuine quantum non-locality, make subtly different predictions when you measure the particles at different angles, in different orientations, not the same predictions, different ones. And the difference, though small, was measurable. Bell's theorem did not say which picture was right. It said that the question was no longer philosophical, it had become experimental. The tests began in the 1970s. They continued through the 1980s and beyond, growing more precise and closing more loopholes with each generation. And the results, consistently, favored quantum mechanics, not hidden variables. Not Einstein's preferred resolution. The correlations were too strong. Stronger than any local hidden variable theory could produce. The particles were not carrying secret instructions. Or if they were, those instructions would have to be coordinated in a way that itself requires something non-local, something that connects distant regions of space in a manner that local realism cannot accommodate. Einstein's intuition, for all its depth, did not survive the experiments. And yet, entanglement does not allow faster-than-light communication. This is worth holding gently for a moment. The correlations are real, and they are instantaneous, but they cannot be used to send a message. The outcome of each measurement is still random. You cannot control what result you get, only observe it. And without that control, the correlation between distant particles carries no information from one place to the other. The non-locality is real, but it is strangely quiet. It does not announce itself. It does not move anything. It simply means that the world, at the quantum level, is not made of separate independent pieces in the way that common sense suggests. Two particles, once entangled, remain part of a single description. Separated by any distance, they are still, in some sense, one thing. That is not a metaphor. It is, as far as the experiments can tell, a feature of the world. There is another thread here, softer and closer to ordinary experience. If quantum superposition is real, if particles genuinely exist in multiple states at once until measured, then why does none of this appear in the world around you? Why does the chair hold its shape? Why does the floor stay solid? Why do the objects of daily life never seem to flicker between possibilities? The answer that physicists developed, slowly, through the 1970s and 1980s, is called decoherence. It begins with a simple observation. A quantum system does not exist in isolation. Every particle, every atom, every molecule is constantly brushing against its environment, against air molecules, against photons, against the faint vibrations of surrounding matter. Each of these interactions is itself a kind of measurement. Each one leaks a small amount of information about the system's state into the surrounding world. And as that information spreads outward, something happens to the wave function. The interference terms, the mathematical threads that allow a particle to be in two places at once, to pass through both slits, to exist in superposition. Those terms do not disappear. Exactly. But they become entangled with an enormous number of environmental degrees of freedom. They spread so thin across so many particles that they become effectively unobservable, practically unreachable, gone for all measurable purposes. This is decoherence. It is why a grain of sand does not produce an interference pattern. It is why a chair does not exist in superposition between two positions. The chair is interacting with the air around it, with the light falling on it, with the floor beneath it, with countless particles every fraction of a second. Each interaction entangles the chair's quantum state with the environment a little more. The superposition does not survive long enough to be observed. The quantum world does not vanish as things grow large. It simply becomes too entangled with everything around it to show its quantum nature. Decoherence is a genuine and important insight. It explains, with real mathematical precision, why the classical world looks the way it does, why large objects behave like large objects. But it does not fully close the question. Decoherence explains why the interference terms become unobservable. It does not explain which outcome actually occurs. It does not say why. When you open the box, you find one thing and not another. The wave function, under decoherence, branches into components that no longer interfere, but all the components are still there. In the mathematics, the theory does not select one. That selection, that single, definite outcome, remains unexplained. Decoherence quiets the quantum world. It does not resolve it. And so the measurement problem, patient and unchanged, remains. The night is very still now. There is a thought experiment that Erwin Schrödinger wrote down in 1935. He was not trying to describe something real. He was trying to show how strange the Copenhagen interpretation had become. In the thought experiment, a cat is placed inside a sealed box. Inside the box, there is a small amount of radioactive material, a single atom, perhaps, that may or may not decay within the hour. If it decays, a detector triggers a mechanism that releases a poison. If it does not decay, the cat lives. The atom's decay is a quantum event. Before measurement, quantum mechanics describes it as being in superposition, neither decayed nor undecayed, but both at once, held in a kind of suspended probability. And if the atom is in superposition, then the detector is in superposition, and the mechanism is in superposition, and the cat, by the same logic, is in superposition. Alive and dead, simultaneously, until the box is opened. Schrödinger found this conclusion absurd. He was not celebrating it. He was pointing at it the way you might point at a crack in a wall, quietly, carefully, to say, something here does not hold. The Copenhagen interpretation, as Bohr and Heisenberg had developed it, said that a quantum system has no definite state before measurement, that the wave function is the complete description of reality, not a map of something hidden beneath. And Schrödinger was asking, gently but precisely, at what point does the quantum world become the ordinary one? At what point does superposition end and a single outcome begin? The cat thought experiment did not answer that question. It sharpened it. It made the measurement problem impossible to look away from, because now it was not an electron in a laboratory, it was a cat in a box. Something large enough to touch, warm enough to hold. And the mathematics said it had no definite state until someone looked. Schrödinger did not believe cats could be in superposition. He believed the theory was incomplete, that something was missing from the equations, some mechanism that would explain how the quantum world gives rise to the definite, solid, singular world we actually inhabit. That missing mechanism has not been found. Not yet. The cat remains, in a sense, still in the box, not literally, but as a question that has never been fully closed. And so we return, as we always do, to the measurement problem, to the gap between the smooth, continuous evolution of the wave function and the sudden, definite outcome that appears when something is observed. Decoherence, as we have seen, goes some distance toward explaining this. When a quantum system interacts with its environment, with air molecules, with photons, with the countless particles that make up the world around it, the interference terms in its wave function become effectively unobservable. The different branches of the superposition stop talking to each other. They no longer interfere. They behave, from the outside, as if only one of them exists. This is why large objects appear classical, why a chair does not flicker between positions, why the moon does not spread itself across the sky in a haze of probability. The environment is always watching, in a sense, always interacting, always entangling. And that constant entanglement suppresses the quantum behavior before it can manifest at the scale we can see. Decoherence is real. It is mathematically precise. It is one of the genuine achievements of 20th century physics. But it does not tell us which outcome occurs. It explains why the branches stop interfering. It does not explain why we find ourselves in one branch and not another. The wave function, even after decoherence, still contains all the possibilities. The mathematics does not reach in and select one. That selection, that single, quiet, definite fact of what actually happened, remains outside the equations. The night holds that question without urgency. There is another strange corner of quantum mechanics worth resting in for a moment. It concerns what happens when you watch a quantum system very closely, not just once, but again and again in rapid succession. Under ordinary circumstances, an unstable quantum system, an atom on the edge of decay, for instance, will evolve over time. Its wave function shifts gradually, the probability of decay growing as the moments pass. This is the natural, unobserved evolution that the equations describe. But if you measure the system frequently enough, something unexpected happens. The decay slows. In some cases, it stops almost entirely. This is called the quantum Zeno effect, named after the ancient philosopher who argued, in a different context, that motion itself might be an illusion. The name is apt, in its quiet way. Each measurement, each interaction that extracts information about the system's state resets the wave function back toward its starting point. The system is, in a sense, interrupted before it can evolve, caught mid-change and returned to where it began. Observation, here, does not merely record what is happening, it prevents it from happening. This is not a theoretical curiosity. It has been demonstrated in laboratories with real unstable atomic states, where increasing the rate of measurement measurably slows the rate of decay. The effect is real, and it is confirmed. And it deepens the strangeness of the observer effect in a new direction. We already knew that measuring which path a particle takes destroys the interference pattern. We already knew that the act of gaining information changes the outcome. But the Zeno effect shows something further, that the rhythm of observation, how often, how rapidly shapes the evolution of a quantum system in time. Not just what you find when you look, but how the system moves, or fails to move, between your looking, there is something almost meditative in this. The system, left alone, changes. Watch too closely, it cannot change at all. There is a pace of attention that allows the world to unfold, and a pace that holds it still. The universe, at its smallest scales, is sensitive to being watched in ways that have no parallel in ordinary experience. And yet, the watching need not be conscious. This is worth holding gently. The observer in quantum mechanics is not a mind, not a person, not awareness in any philosophical sense. It is any physical process that records information, a detector, a photon scattering off a surface, a molecule brushing past another molecule. The universe does not require a witness in the human sense. It requires only an interaction that leaves a trace. That distinction matters, and it is also, in its own way, strange, because it means the question of what counts as a measurement, what counts as an observation, is not yet formally defined within the theory, the boundary between the quantum system and the measuring apparatus, between the thing being observed and the thing doing. The observing is drawn differently by different interpretations, and no experiment has yet told us where the line truly falls. The equations work. They work with extraordinary precision, to more decimal places than almost any other theory in science. They predict, and the predictions are confirmed again and again in laboratories around the world. But the equations do not say what is happening. They say what will be found when something is measured. They do not say what exists in the silence between measurements. That silence is where the mystery lives. And it is very quiet now. There is a way of listening to a quantum system without quite asking it a question. Physicists call it weak measurement. It is a technique that touches a particle so gently, so briefly, that the wave function does not fully collapse. The system is nudged, not interrogated, and what comes back is not a sharp answer, but a whisper, a partial impression, blurred at the edges, carrying only a fragment of information. No single weak measurement tells you much. The result is too faint, too uncertain to be trusted on its own. But when you gather thousands of them, each one a soft breath against the quantum state, something begins to emerge from the accumulation. A shape, a tendency, a path. And when physicists applied this technique to the double-slit experiment, what they found was quietly remarkable. The particles, nudged so gently that their interference pattern was preserved, seemed to trace smooth, curving trajectories through space. Not the sharp, definite lines of a classical object moving from one place to another, but something softer, something that bent and flowed around the slits, that curved away from the dark bands and gathered toward the bright ones. Trajectories that looked, in their overall shape, very much like the paths that pilot wave theory had predicted decades earlier. This does not prove pilot wave theory. It is important to say that clearly. Weak measurement reconstructs average behavior across many particles, not the true path of any single one. The resemblance is suggestive, not conclusive, but it is the kind of result that sits with you, that makes you wonder whether the wave guiding the particle might be, in some sense, more than a mathematical convenience. The silence between measurements may not be entirely empty. And yet other physicists look at the same experiment and draw a very different lesson. Carlo Rovelli, a physicist who has thought carefully about the foundations of quantum mechanics for many years, arrived at an interpretation that begins not with particles or waves or branching worlds, but with a simpler and more unsettling question. What if quantum states are not properties of a system at all, but properties of a relationship? His proposal is called the relational interpretation, and its central idea is this. A particle does not have a definite state in any absolute sense. It has a state relative to something else, relative to a detector, or a measuring device, or another particle, or any physical system that interacts with it. The wave function is not a description of what the particle is. It is a description of what the particle is, from a particular point of view. Two observers, interacting with the same particle in different ways, may assign it different quantum states, and both may be correct. Not because reality is subjective, but because quantum states are relational. The way velocity is relational. A stone is not fast or slow in any absolute sense. It is fast relative to one thing and slow relative to another. Ravelli suggests that quantum states work the same way. This is a quiet but radical idea. It does not require parallel worlds. It does not require a pilot wave filling all of space. It requires only that we let go of the assumption that a particle carries its properties with it, independently, wherever it goes. The universe, in this view, is not made of things with properties. It is made of interactions, each one defining something real, but only relative to something else. There is another interpretation that takes a different kind of step inward. Cubism, sometimes called quantum Bayesianism, begins not with the particle, but with the person, or more precisely, with the agent, the one who is making the measurement, forming the expectation, updating the belief. In cubism, the wave function is not a feature of the world. It is a representation of what an agent believes, a compact encoding of expectations about what will happen when a measurement is made. When the measurement occurs and an outcome is found, the wave function updates, not because something in the world collapsed, but because the agent learned something and revised their beliefs accordingly. This might sound like it reduces physics to psychology, but its proponents argue the opposite. They say it is the most honest account of what quantum mechanics actually does. The theory has always been a tool for predicting outcomes of experiments. Cubism simply takes that seriously and stops pretending the wave function is a map of something out there, waiting to be discovered. The world, in cubism, is real. The outcomes of measurements are real. But the wave function belongs to the agent, not to the universe. It is a strange kind of comfort, perhaps, or a strange kind of loneliness, depending on how you hold it. And here's the thing that makes all of this so difficult to resolve. Every one of these interpretations, Copenhagen, many worlds, pilot waves, relational, cubism, and the others that have been proposed over the decades, makes exactly the same predictions. Every single one. You cannot design an experiment that would return a different result under one interpretation than another, because they all agree on what will be measured. They disagree only on what that measurement means, on what is happening, or whether that question even has an answer. Decades of debate. Some of the sharpest minds in the history of science, thinking carefully, arguing carefully, writing carefully, and no experiment has yet drawn a line between them. This is not a failure of science. It is something stranger than failure. It is a situation in which the theory works perfectly, and the question of what the theory is about remains genuinely open. Some physicists find this acceptable. The predictions are what matter, they say. The rest is philosophy. Others find it deeply unsatisfying. They believe that a complete theory of nature should say what nature is, not only what it will show us when we look. That disagreement has not been settled, and it may not be settled soon. There are those who hope that new experiments, in new conditions, might eventually break the symmetry, might find some small difference, some subtle deviation that points toward one picture and away from the others. One direction that has drawn quiet attention is the question of gravity. Quantum mechanics and general relativity, the theory of gravity, have never been fully reconciled. They are both extraordinarily successful in their own domains, and they do not agree with each other at the deepest level. Some physicists have wondered whether gravity might affect quantum interference in some way that the standard theory does not predict, whether the curvature of space-time might leave a trace in the double-slit pattern. To test this, versions of the experiment have been designed for space-based platforms where gravitational conditions differ from those in a ground laboratory. The results are still being gathered, still being analyzed. No clear signal has emerged yet, but the question is being asked with real instruments, in real conditions, and that is something. The experiment that Thomas Young performed with a candle and two narrow slits in 1801 is now being performed in orbit. The question has not changed, only the altitude. And somewhere tonight, in a laboratory that is very quiet, the experiment is running. A particle is moving through the apparatus, The slits are open, no detector is watching, and the pattern, slow and patient, is building itself one arrival at a time on the screen. It does not know it is mysterious. It simply continues. There is one more thread to follow before the night grows fully still. Some physicists, over the decades, have wondered whether the missing piece is not a detector, not an environment, not a branching of worlds, but something closer to home. They have wondered whether consciousness itself plays a role. The idea is not new. It surfaced in the early days of quantum theory when the strangeness of measurement was first being confronted. If the wave function collapses only when observed, and if no physical process in the equations describes that collapse, then perhaps, some reasoned, the observer must be something more than a machine. Perhaps awareness itself is what draws a definite outcome from the fog of probability. It is a thought that has a certain quiet appeal, lying here in the dark, and yet it is not where the evidence points. Most physicists do not hold this view. Decoherence, the way a quantum system becomes entangled with its environment, can suppress interference without any conscious mind present. A detector in an empty room, recording which path a particle took, with no one there to read the result, still destroys the pattern. The universe does not appear to be waiting for someone to pay attention. The consciousness interpretation also carries a deeper difficulty. It has never produced a prediction that differs from the standard theory. It cannot be tested in a way that would distinguish it from the alternatives. And without that, it remains a philosophical position rather than a scientific one. Not wrong, perhaps, but not yet reachable by experiment. Still, the question it was trying to answer is real. What counts as an observation? This is not a settled matter. Within the standard formulation of quantum mechanics, the word measurement is used constantly and never formally defined. The theory tells you what happens when a measurement occurs. It does not tell you what a measurement is. It does not specify at what point in a chain of physical interactions the wave function transitions from spreading possibility to definite fact, whether it is the particle striking a detector, the detector triggering an electrical signal, the signal reaching a computer, the computer displaying a number, or a mind registering that number. The boundary is not drawn. And this is not a minor technical gap. It sits at the very center of the theory's foundations. Physicists have worked around it for a century with great success, applying the rules carefully and obtaining answers of extraordinary precision. But the gap remains, quiet and unresolved, beneath all of that precision. Because quantum mechanics is precise, more precisely confirmed than any other theory in the history of science. The magnetic moment of the electron, a measure of how strongly it responds to a magnetic field, has been calculated using quantum theory and measured in the laboratory. The two values agree to more than 10 decimal places. 10 decimal places. That is the equivalent of measuring the distance from here to the far side of the continent, and being accurate to within the width of a human hair. No other framework in physics, in all of its history, has achieved anything close to this. The predictions of quantum mechanics have been tested in particle accelerators, in atomic clocks, in the behavior of semiconductors, in the structure of chemical bonds, in the glow of distant stars. Every time, the theory holds. Every time, the numbers match. And yet, the theory that achieves all of this cannot say, in plain language, what is actually happening when no one is looking. It can tell you the probability of finding a particle here rather than there. It cannot tell you where the particle is before you look. It can describe the interference pattern with perfect accuracy. It cannot tell you which slit the particle passed through when no detector is present, not because the information is hidden, but because, under most interpretations, the question has no answer until the moment of measurement. The most successful quantitative theory ever constructed is, at its foundations, silent on the nature of reality between observations. This is not a failure of effort. Generations of the most careful thinkers in physics have turned their attention to this silence. Bohr accepted it as the natural boundary of what science can ask. Everett tried to dissolve it by letting every outcome be real. Bohm tried to fill it with a wave that guides particles along definite paths. Rovelli suggested that reality itself is relational, that there is no view from nowhere, only views from somewhere. Each of these answers is coherent, each carries its own strangeness, and none of them has been separated from the others by experiment because they all predict the same numbers. The silence remains. At the center of all of it, the interpretations, the theorems, the entanglement, the erasure, the delayed choices, the branching worlds, the pilot waves, the orbital experiments still gathering data. At the center of all of it sits something very simple. Two narrow slits, a source of particles, a screen. Thomas Young arranged something very much like this in 1801, working with light and patience in a room that is long gone. He was trying to settle a question about the nature of light. He settled it, for a time, and then the 20th century reopened it and deepened it, and found that the question was not only about light, but about the nature of reality itself. The double-slit experiment has been running, in one form or another, for more than 2 centuries. It has been performed with light, with electrons, with neutrons, with atoms, with molecules large enough to contain thousands of atoms. It has been performed with detectors and without them, with erasure and without it, with the measurement choice delayed until after the particle was already in flight. It has been carried into orbit. And every time, it gives the same answer to the same question. When you do not watch, the particle behaves as a wave, spreading through both slits at once, interfering with itself, building a pattern of light and shadow that has no explanation in the language of ordinary objects moving through ordinary space. When you do watch, the pattern vanishes. The particle chooses a path. The wave becomes a dot. The question the experiment is asking, has always been asking, is this: what is the particle doing when no one is looking? And the honest answer, after more than 2 centuries of increasingly careful asking, is that we do not know. The theory does not say, the interpretations disagree, the experiments cannot yet distinguish between them. This is not a comfortable place to rest. And yet there is something in it that is not troubling if you let it settle slowly. The universe is under no obligation to be fully legible to the minds that have arisen within it, that those minds have gotten as far as they have, that they have mapped the interference fringes, derived the uncertainty principle, confirmed the magnetic moment of the electron to 10 decimal places, sent the experiment into orbit, is already something close to extraordinary. The question is still open, and tonight, in laboratories that are quiet and carefully shielded from vibration and stray light, the experiment is still running. Particles are moving through the apparatus one by one. The slits are open. No detector is watching. And on the screen, slowly, over hours, the pattern is forming. Bright, where the waves reinforce. Dark, where they cancel. Patient and precise, and in some way that no one has yet fully explained. Deeply, quietly strange. It has been asking its question for a very long time. It is in no hurry, and neither are you. So the pattern forms, and it will keep forming night after night, in one laboratory or another, for as long as there are people who want to understand what matter is doing when no one is watching. That is the question the double-slit experiment has always been asking. Not loudly, just persistently. It began, as so many things do, with light. In 1801, a physicist named Thomas Young passed a beam of light through 2 narrow slits cut into a barrier. On the screen behind, he expected to see 2 bright lines, one for each slit. What he saw instead were many lines, alternating bands of brightness and shadow, spreading outward from the center like ripples from 2 stones dropped close together in still water. This was interference. When the wave from one slit met the wave from the other, they combined. Where crest met crest, the light grew brighter. Where crest met trough, they canceled each other, and the screen went dark. The spacing of those fringes depended precisely on the wavelength of the light and the distance between the slits, a relationship that could be measured, calculated, confirmed, It was, in its quiet way, a proof that light was a wave. Newton had believed otherwise. He had thought light was made of particles, small and fast and definite. Young's experiment suggested he was wrong. And for about a century, that seemed to settle it. Then the 20th century arrived and settled nothing. Einstein showed in 1905 that light also behaves as a particle, the photon, delivering energy in discrete packets when it strikes a metal surface. This was the photoelectric effect, and it was real, and it was measurable, and it earned him the Nobel Prize. So light was a wave, and light was a particle. Both, depending on how you looked. This was not a comfortable conclusion, but it was the one the evidence kept returning to. Then came something stranger still. Louis de Broglie proposed in 1924 that matter, not just light, but actual matter, things with mass, also has a wavelength. The wavelength is inversely proportional to momentum, which means heavier or faster objects have wavelengths too small to detect. But for something as light as an electron, the wavelength is measurable. And measurable meant testable. Electrons were sent through a double-slit apparatus. They produced interference fringes, the same alternating bands Young had seen with light, now appearing with particles of matter. Then the experiment was made quieter still. Single electrons were fired, one at a time, with long pauses between each. There was no way for one electron to interfere with another. They were never in the apparatus at the same time. And yet, over thousands of arrivals, the interference pattern accumulated on the screen, bright where the waves reinforced, dark where they canceled. Each electron somehow had interfered with itself. This is the part that resists easy description. An electron is not a wave in the way that water is a wave. It is not spread across space in any ordinary sense. And yet, when no one is watching which slit it passes through, it behaves as though it passed through both. The mathematics describes this as a superposition, the electron existing in a combination of both paths simultaneously, until something forces a choice. Richard Feynman, who thought about these things as carefully as anyone, said that the double-slit experiment contains the only real mystery of quantum mechanics, that all the other strange results, the uncertainty principle, entanglement, the Zeno effect, are, in some sense, variations on this one thing. A particle that is not quite a particle, a wave that is not quite a wave, something that becomes definite only when it is asked to be. The asking matters. Place a detector at one of the slits, any device that records which path the electron took, and the interference pattern disappears. Not partially, completely. The electrons begin arriving in two simple bands, as if they had always been ordinary particles traveling one path or the other. The detector need not display its result. No one need read it. The mere physical possibility of knowing the path is enough. The information exists somewhere in the world, encoded in the state of the detector, and that is sufficient to dissolve the superposition. This is called the observer effect, though the word observer is misleading. Consciousness is not required. Any physical interaction that records path information has the same result. The universe, it seems, responds not to awareness, but to the availability of information. Erase that information, a procedure called quantum erasure, and the interference pattern can partially return. What matters is not whether the particle was disturbed, but whether its path can, in principle, be known. There are several ways physicists have tried to make sense of this. The Copenhagen Interpretation, developed by Niels Bohr and Werner Heisenberg in the 1920s, holds that the electron has no definite path before measurement. The wave function, the mathematical object that describes the electron's state, is not a map of something hidden. It is the full truth of what exists, and asking what the particle is doing between measurements is, under this view, not a meaningful scientific question. The wave function evolves smoothly, according to precise equations. Then, at the moment of measurement, it collapses, suddenly, discontinuously, into a single definite outcome. How this collapse happens, what causes it, What counts as a measurement? These questions are not answered by the equations. They are added as a separate postulate, and the gap between the smooth evolution and the abrupt collapse is called the measurement problem. It remains open. Hugh Everett proposed a different path in 1957. In his many-worlds interpretation, the wave function never collapses. Every possible outcome of every measurement occurs, but in branching versions of reality that do not interact after they split, when the electron passes through the apparatus, both outcomes happen. In one branch, it arrived here. In another, it arrived there. Both branches are equally real. Neither can reach the other. This requires no special collapse mechanism. The mathematics is clean, but it implies an enormous, possibly infinite, proliferation of parallel realities, each as real as this one, each permanently inaccessible. It is a tidy solution to the measurement problem, and a deeply strange one. David Bohm offered something different again. In pilot wave theory, the electron always has a definite position. It always travels one path, but it is guided by a real physical wave, the pilot wave, that fills all of space and passes through both slits simultaneously. The wave interferes with itself. The particle follows the wave's guidance, and the interference pattern emerges not from the particle being in two places, but from the wave shaping where the particle is likely to go. This restores something like ordinary reality to the electron. It has a path. It has a position. But the pilot wave responds instantaneously to changes in the experimental setup, including the opening or closing of a slit across any distance, without delay. This non-locality does not allow faster-than-light signaling, but it requires a kind of instantaneous connection woven through space, which carries its own strangeness. 3 interpretations, each internally consistent, each in agreement with every experiment ever performed, each describing a fundamentally different universe. And no experiment has yet been able to distinguish between them. This is where the theory stands tonight, precise, beyond almost any other achievement of human thought, and yet silent on the question of what is actually there. The electron moves through the apparatus. The slits are open. No one is watching. And somewhere between the source and the screen, something happens that the equations describe perfectly and that no one, not yet, has fully explained. The pattern is still forming. Slowly. Patiently. As it has been, in one form or another, for a very long time. There is one more thread to follow, before the silence comes. It begins with a question that sounds almost too simple to matter. What counts as a measurement? In ordinary life, a measurement is something a person does. A scientist reads a dial. A scale registers a weight. But in quantum mechanics, the boundary between measuring and not measuring has never been formally defined. The equations do not say what qualifies. They do not say how large a system must be, or how irreversible an interaction must become, before the wave function gives way to a single outcome. This is not a minor gap. It sits at the center of the theory, the most precisely tested theory in the history of science, like a room no one has been able to enter. Some physicists have suggested that consciousness itself might be what collapses the wave function, that awareness, in some fundamental sense, is what transforms possibility into fact. This view is not widely held. It lacks experimental support, and most physicists are cautious about it. But the fact that it can be proposed at all, that it has not been ruled out, says something about how deep the uncertainty runs. The question remains open. What is an observer? A detector? A photon? A molecule of air brushing past an electron? At what point does the quantum world become the ordinary one? No one has answered this cleanly, and yet the theory built on top of this unanswered question predicts the behavior of atoms, the structure of molecules, the properties of materials, the behavior of light, all of it confirmed, again and again, to more than 10 decimal places, numbers that precise are almost beyond imagining. A prediction accurate to 10 decimal places is like measuring the distance from here to a distant city, and being correct to within the width of a single hair. The theory works extraordinarily well. And still, it cannot say, in plain terms, what is happening when no one is looking. There is something almost restful in that, a reminder that understanding and usefulness are not the same thing, that a map can guide you perfectly through a landscape whose nature remains, at some level, unknown. Decoherence brought some clarity to part of this. When a quantum system, an electron, a molecule, a superposition of states, interacts with its environment, the interference between its possible states becomes effectively invisible. The surrounding air, the walls, the faint electromagnetic fields, all of it entangles with the system, spreading the quantum information outward until it is too diluted to detect. This is why a grain of sand does not visibly interfere with itself, why a chair does not exist in superposition between two positions in a room. The quantum behavior is still there, in principle, but it has dissolved into the environment, beyond any practical recovery. Decoherence explains why the world looks classical, why large things behave like large things. But it does not resolve the deeper question. It does not say which outcome occurs. It only explains why the others become invisible. The measurement problem remains, quieter now, but still present. There is a technique called weak measurement that approaches this from another direction. Rather than asking a quantum system a sharp question, forcing it to declare a definite state, weak measurement asks something softer. It extracts a small amount of information, leaving the wave function mostly intact. And when many such gentle measurements are combined, they trace something that looks, approximately, like a path. These reconstructed paths resemble the trajectories that pilot wave theory predicts. Not identical, not proof of anything, but suggestive. A hint that the question of what the particle is doing between measurements may not be entirely beyond reach. The experiment continues to yield new things, even now. In 2019, researchers produced interference fringes using molecules containing roughly 2,000 atoms, objects that large, behaving as waves. The boundary between quantum and classical pushed a little further than it had been before. No one knows yet where that boundary finally lies, or whether it lies anywhere at all. Some interpretations suggest it does not, that the wave function never collapses, not truly, that every outcome occurs, branching silently into versions of reality that never meet again. Others suggest the wave function is not a feature of the world at all, but a way of encoding what one system can expect from another, a language of relationships rather than a map of things. Carlo Rovelli proposed that quantum states are not absolute, that they exist only relative to a particular observer or system, that there is no view from nowhere, no description of the electron that stands apart from every possible interaction with it. Reality, in this picture, is woven from relationships rather than from objects. Cubism takes a different step. It treats the wave function as a representation of an agent's beliefs, a tool for updating expectations, not a picture of the world. A collapse, in this view, is not a physical event. It is a revision of belief in the light of new experience. Each of these pictures is coherent. Each survives every experiment. Each describes a different kind of universe. And no measurement yet devised has separated them. This is where physics stands tonight, not in failure, but in a particular kind of openness. The equations are trusted completely, the predictions are confirmed without exception, and the question of what the equations are describing remains, gently, unanswered. The double-slit experiment sits at the center of all of this. A screen, two narrow openings, a source of particles, one at a time. It has been running, in one form or another, for more than 2 centuries, first with light, in a room in the early 1800s, then with electrons, then with atoms, then with molecules large enough to see in certain instruments. Each time, the same result. Each time, the same quiet refusal to be explained away. The pattern forms, slowly, each particle arriving alone, touching the screen at a single point, giving no sign of what it passed through. And yet, over time, the points accumulate into something that could only have come from a wave. Bands of arrival and absence, spaced with mathematical precision, shaped by interference between paths that no single particle seems to have taken. It is still running tonight. In laboratories in several countries, in configurations Thomas Young could not have imagined, the experiment continues. Researchers are testing whether gravity affects quantum interference, whether the effect persists across greater distances, whether something in the structure of space-time leaves a trace on the pattern. The results are still being gathered. The analysis is still underway. The question is still open. And somewhere in a quiet building, in the middle of the night, a detector is registering arrivals, one by one, each one a point of light on a surface, each one part of a pattern that is slowly, patiently, becoming visible. The electron does not know it is being counted. The wave does not know it is being watched. And the pattern forms anyway, as it always has. Bright where the waves agree, dark where they cancel. The same result every time for as long as anyone has looked. And the question it carries, what is the particle doing when no one is watching, drifts on, unanswered, into the dark? The screen is still there. The slits are still open. And somewhere between the source and the surface, something is happening. Quietly, patient as ever, still forming.